Okay, so I think most of you have been here before, so Just Enough Math, we're here to present ideas and concepts that can aid in solving problems, especially around development. My name is Ahmed, and I'm a developer here at Improving. And also presenting our case study is Kai. Can you introduce yourself?
Hello, I'm Kai, and I do automated trading systems.
Yeah, so he'll be giving us a case study. Yeah.
Yeah.
See.
And the case study is predictions using Sine in Sine theory.
Cool, thank you. And so yeah, so today we're going to talk about line curve fitting. As a reminder, all of our coded presentations are available through Colab Notebooks. I pasted a link in LinkedIn, Just Enough Math group. Anyone who needs a link, just let me know. Once you access it, you can play around with the examples, change them, use the code, all that fun stuff. Okay? Okay. So quick intro. So line or curve fitting, I might just start calling it line fitting just to save my breath. It's pretty much a way of fitting a function to data, okay? So the idea is that you have a bunch of data points. You assume there's some relationship between a bunch of data points and one particular output, right? And so you try to find what function can actually fit these points as best as you can, okay? And you could use lines or you could use curves, and ideas that once you have that, then you should be able to make predictions based on the data and even analyze to understand the relationship. Okay. Now, fits are not going to be perfect, so there's this idea that there's noise in your data. Maybe the noise has to do with measurement and precision, maybe errors in recall. And you might even have additional conflating factors, variables that you did not account for. Okay? But the idea, at least, is that if you assume that noise is some accidental, random perturbations in your data, you might consider your prediction line, even though it doesn't fit everything, to be the best fit, because it may be your true function. Whether that's an overly idealistic assumption, it's an assumption some folks make. And we're going to get into some code, show you some examples, but just to give you like a high-level example, for example, assume that you're trying to sell a house. You're trying to figure out, what price will your house sell for. And you have data on homes that have already been sold along with their prices, right? So you have info like square footage, number of bedrooms, and so on. And then you have how much did the house sell for. And so you'd be trying to figure out how does the square footage, number of bedrooms, and so on contribute to the price of the house. And can you make a prediction and even figure out which factors, how much does each factor contribute to the price of your house? Which can then help you make decisions like, how should you remodel your house to get the best return on your investment? And we're going to show you a synthetic example of that. Okay? So any questions so far? Okay. And a lot of stuff, again, this is pretty much a simple form of machine learning. So essentially this sounds familiar to what machine learning does. Well, there's a reason, right? You're still fitting algorithms to data, you're making predictions.
You're minimizing an error, right? That's what
Yes.
a lot of machine learning algorithms do.
Exactly.
Yeah, you lay out. So you have a prediction, and you have associated with a data point, and you have the difference between the prediction and the reality, and that's an error. And somehow, for each data point you have this error, and somehow you summarize that in one big error. And that's a function, and you minimize that.
Yeah.
So it's just one more example of that type of thing.
Exactly. It's an optimization problem at the end of the day. Yeah, absolutely. Yeah. And so linear regression is probably the simplest version of this kind of fitting. And really what it is you find an equation, okay, of the form, some coefficient, I'm calling W for weight, times each one of, times your variable, one of your variables of interest, and you sum it up. So you're going to have a different coefficient for each one of your variables. You're going to sum them all up, and you're going to add a constant to it. And so the idea is that you try to find all of your W's and your B, and what you're trying to optimize, what you're trying to minimize, I saw you chuckle there, Nick. What you're trying to minimize is basically the sum of the squared error. And error here is just you have a prediction, you have the actual value, you subtract them, you square them, you sum all those up, and whatever sets of W's and B, go ahead and minimize that, that becomes basically your best fit. Now different types of fits are going to use different like error metrics, different types of machine learning will, but this is what linear regression at heart does, okay? And there's packages that do that. So at the end of the day, I just use a package. And it's called linear because you're essentially going to have a line that fits your data, or if your data is in higher dimensions, some kind of hypersurface and hyperspace. Why is it hyper? Yes?
So why does it have to be squared?
So two reasons. The first, it's a way of ensuring, of course, you're not going to have negatives. But the second also is I think it tries to amplify the impact of any errors. Justin, did I speak out of turn here? Why are we squaring the error?
It doesn't have to be squared, like, but
Use actions.
you can use, there's like a whole family of,
Because it's just the easy, actually, because it's the easiest to calculate.
Yeah, it has the advantage of being differentiable. So like, you could, absolute value would make sense, but it's not completely fully differentiable, so you can't use the calculus-based techniques to optimize.
there are other exponents you could use though to still be differentiable, but I don't know, the square is like, but yeah, I mean the absolute value, but the square is like, I think it's just kind of traditional because like it coincides with our notion of like regular distance in Euclidean space.
I think there was a proof
Oh, I
that,
see.
no, I think there
Yeah,
was a proof
you
that
can dissect it into A plus.
it's the best, it is the best estimator
Yeah.
for normally distributed, assuming your errors are normally distributed, it is supposed to be the best estimator out there.
What is it?
But it's not the best in practical sense because it's very susceptible to outliers. Like if you have a line, you have a bunch of dots, and then you have a data point way up there,
Yeah.
that will completely skew the.
So it'll
and,
maximize that.
and there are better estimators that minimize the skewness from outliers.
Yeah.
But assuming that it's normally distributed with not outliers, it's supposed. It was proved to be the best.
It's the square, I mean,
B square. Yeah. For normally distributed errors.
so normally distributed, it's not,
Yeah, the square does increase the impact of an error, so those outliers are going to hose you get that wrong. Cool. That's interesting. And then there was actually proof that
And
was
also,
the best.
it's the easiest to.
Most important reason.
It's computationally efficient too.
Yeah. Cool. Awesome. So so basically, so again, I mean, with a linear regression, you can predict and you extrapolate data, interpolate, extrapolate, and you can get an equation to see the impact of each variable. It's an easy to understand equation, right? It's nothing with anything like, crazy polynomials or a whole bunch of layers with activations like a neural network. It's always quite tractable. Use your function, you can use as your data points provided you don't mind the idealized view of your data. And again, assuming that the difference in your data is noise, and again, that's a bit of a perhaps generous assumption, it can help you identify like what the true relationship in your data is. Simple to build, easy to understand, right? But it's not a good fit for complex patterns. It assumes that your data forms some kind of line without any kind of change in slope or oscillations. So here's an example of linear regression. I'm going to show you the code just briefly. So again, this is fairly straightforward. This is Python. There's already a function for it. So all I'm doing here is I'm just generating some random data, and then I'm just basically having y be that random data along with a little bit of perturbation, right? Because I want to make it a little bit interesting. But in reality, the data is being synthetic, so there's an obvious relationship between x and y. Okay. And again, the data is kind of drawn from the normal distribution, but doesn't really matter. It's a small amount of noise added. So we just call linear regression to instantiate a linear regression model. We tell it to fix x. X is the input data to predictors. Y is your output. And then once we fit the model, we now have a linear regression model that we can use to predict. And to predict it, we call predict. And that gives us a set of predictions. And then here I'm just plotting them. Okay? Scatter blue okay? That's our original data. The red line is our linear regression, our fit, best fit according to linear regression. And so you can see here what the fit looks like. Okay? Again, this is highly contrived data, and in more realistic linear regressions, you're gonna have a harder to find fit, and you have to kind of squint to see that, oh, this is kind of a fit. But even here you can see that, you're not gonna hit most of your points. You're trying to find this area where you're minimizing the error, but you're not really intersecting a lot of these points. Okay, so far so good?
Can we just
Squeeze it.
visualize what the error is since we were on,
Question?
since we were on the topic?
Sure.
I said, what's squeeze do?
Oh, squeeze is basically like flatten. When Python when we generated data, it basically generated an array of arrays, but each array had just one element. So basically kind of did a flatten. That's all it does. Yeah.
Is there what? I was wondering about that.
Yeah. So this basically so when this generated the data, it generated an array of arrays. It was really just a 1D array, but each element was basically its own array. So this essentially flattened it out into just an array. It kind of removed the inner arrays. That's all it did. It's like a flattened function, really. Squeeze is a really crappy name in my opinion, but no one asked me.
Squeeze.
Yeah, squeeze. I'm like, yeah. So yeah, that's all. It's flat.
Oh, okay.
Yeah. So Justin, you wanted to talk error?
Well, I just wanted to, just make it entirely clear since we're on the topic. So when we talk about like the least square error, right? They use this the error instead of error. They often talk about residuals, right? So, well, not instead, but so the residual. Those are actually two different things, I guess. So the residual is always the vertical. This vertical difference here between this point on the line and this this data point, and it could actually, the residual could also be negative, right? So like, for example, it depends on, just because you're just subtracting, right? So you're subtracting a value on the line, right, a y value on the line, and then minus the y value of the particular data point, right? So that could be negative, but when you square it, it becomes positive. So you basically, for every data point, you take that difference, you square it, and you sum that up. That's your error. Well, you take the square root, and then also don't you divide by n or something, I guess. So, well, the way I do the data is I just call it linear regression.
It's kind of like normalized within the dimension of the regression, of how many points you have, right? The square root of
Isn't it?
all of the things, of all the residuals squared.
But I guess
Is there a normalization?
but it doesn't matter. Well, I mean,
the final division that you were talking about.
Oh,
I think finally you would divide by n, right?
because you're getting the mean, right? Yeah, 'cause you're getting the mean.
Yeah,
Yes.
that's why it's called the mean squared error, right?
Yeah.
Yeah.
So that's what your division is, yeah.
Yeah. So it looks like a big radicant with a bunch of squared things that
Yeah.
all over n. Okay.
Yeah.
Huh? Yeah, it's the mean squared error. So, but I mean, dividing by n doesn't change the function, right? 'Cause you just multiply. I mean, minimizing 1 is the same as minimizing if you divide by n. Same goes for taking the square roots. I don't know actually how the computation runs in practice, though. They do those things. Anyway, so
You guys should do it too.
I have it somewhere in code, in the packet patches that I wrote, but I can't remember from the top. Yeah, I wrote all that stuff in the source
Oh, okay.
for the Python package. So, but I can't remember from the top.
I didn't do a very one for giggles just using like linear algebras, like multiplying and transpose and inverted and multiply, but it was fun, but it's like a one-liner. Okay. Yeah.
Fun.
Yeah, that's what I do for fun, folks. I have no life. I admit it. Happy?
One-liners are the best.
Well, we'll have to talk after. There's a conversation we had. So, okay. So yeah, so pretty much, and again, a lot of times the assumption is that, hey, these points may represent some noise, okay? And so this might be more of the true phenomena, but again, maybe these points are where they are because there's additional variables we don't know about. So, and this again, this is just like a one data point, X versus Y. So let's look at like a multivariate one and see how we can kind of, use the equation, okay, that the linear regression gives, because we can get an equation back from it. So here's again another contrived example of home price data, okay? So essentially, I'm just cooking up some random values for home price, for random values for home attributes, number of rooms, like number of bedrooms, square footage, how old your roof is, that sort of stuff, okay? And I'm just generating some random values for all of them. And then basically, I'm going ahead and again, just creating a price that's just a function of these different factors, essentially weighting them positively, negatively, depending on whether or not they're desirable or not. And then again, perturbing them with a bit of a noise, okay? And again, this is just to show, to make the example really, really obvious that I want to show you, okay? So don't base your home prices on these, this is all manufactured. So after generating this data of basically home attributes and prices, again, do a linear regression, home attributes, right? Fit the home attributes to prices. We predict the prices by just basically running a prediction on home attributes. And I'm just rounding them just to kind of, make the numbers a little nicer to look at in the data frame. And again, you can see here that we have our actual predicted. Again, since the relationship is very strong, the ratio throughout it all is, of course, very close to 1. So far, so good. Now, but what makes this a little bit more interesting is that we can spit out a formula. So we can look at our model and tell it, hey, spit out our coefficients, okay? And also give me the intercept. The intercept is the constant that we add to our linear regression. And I call it the intercept because in a two-dimensional case, it's supposed to be the y-intercept, where the line hits your y-axis. And I'm just saying, hey, spit it out in the form of a nice little formula here, and print this formula out. And we can see right here that there's the formula. So this tells us, hey, we're predicting your home prices within a very high degree of accuracy using this formula. Now, x0 is the square footage of your house. X1 is the number of bedrooms. X2 is the number of bathrooms. Then it's like, I believe, the age of the roof and the age of the house. Now, looking at these factors, what can you say about home prices? Like, what variables are most important here? Yeah, X0, this is America. X0, sir. But anyway, so X0. Well, yeah, because that's like what it's about 10,000. Every square foot in your house contributes about $10,000 to the price, right? And again, it is manufactured, but it shows you at least the impact, right? You can see you get about $916 for every extra bedroom, and you can see that there's actually a negative impact on some of the other factors here, right? Like the age of your house has a negative impact, as does your roof, right? So I mean, if you're looking to try to like remodel your home to get the best price, you can use this equation to kind of decide what gets you the best bang for the buck. I don't know, can you add another wing to your house really cheaply? Duct tape some cardboard, claim you have an extra 10 square feet, I don't know. I'm not a real estate agent, don't take this as advice. just so like, don't come after me if you try this and someone comes after you. But at least you see like what's an impact of your business. I mean, math just gives you answers. What you do with it is your problem, right?
If you run an extension cord from like your kitchen out to the RV in your front yard, there's a third bathroom or bedroom, I guess.
Yeah, exactly.
I'd love to see you try to pull that off. That would be kind of.
So it's $12,000.
Yeah. But here's the thing: if every bathroom,
Redneck real estate.
we get it.
What about when you paint all your walls gray? The agreeable gray.
The agreeable gray.
Well, you have to figure out a way to quantify that.
Yeah, that's true.
Yeah.
That's the other thing. Lots of like millionaires who have their houses, they're not sellable in the market. When they're selling, when they try to sell their in the movie theater, when they try to sell their houses, people are not buying the house; they're just buying the land because their tastes are so eccentric. It doesn't apply to.
Like the odds of finding someone who can afford that house and who actually would like it and live there are very low.
Well, and
raise
now what
it
they're trying to
for
do
something
is,
else.
like in California, they're adding the mansion tax. Did you hear about that? So people are trying to sell their mansions. They're giving away all their exotic cars just to sell the mansion as well.
Wow.
With the cars come with the mansion?
He's like, yeah, yeah, buy my mansion. You get this McLaren F1. You're like, oh, okay,
But
sure.
also, Nick, your idea about the RV, according to our linear regression formula, that's a bad idea. Because every bedroom only contributes $916. Your RV is probably worth more. You just say you get a free RV with a house that's at $10,000.
Exactly.
So there you go.
That's like how you find RV. Wrong factor. Wrong factor. You need new facts.
What's the definition of recreation?
The redneck definition. Recreation.
Doors open, man. So the problem with linear regression, though, is that, again, it assumes that your data basically forms some kind of like straight line, essentially, right? That it grows in some kind of straight path. Not necessarily grows, but essentially forms that. Now, for some long-term trends, you may be able to, in fact, say, yeah, that is true, right? Or for some phenomena, you can say it's true. But sometimes you have phenomena that just basically oscillate, right? Have shapes that are not linear, a curve, a level off. Or maybe they're linear in the long term, but you're interested in predicting in the short term, right? So here's an example of just some cooked up synthetic data. Trying to fit a line to this, you can get your feelings hurt. Yeah, exactly. Because, but that's, that ain't gonna happen, right?
Flat.
Huh?
To me, it would just look like it's flat. Like
Ye-
y equals 0.
We need to have another talk. Yes, there is technically a best fit line that will minimize the error. But that's also saying there's a way of shooting yourself that's going to minimize damage. The line's going to suck, okay? And yeah, a flat line would probably fit it because it probably cancel the error out. But it's not going to tell you anything
You don't
about
want to
the
make
problem.
money from this. This is actually the stock fee.
Yeah.
A flat line is you probably want to do better than a flat line.
Yeah.
I mean, it just depends on what you're trying to do.
I mean, if you're trying to predict this, then you failed.
Oh, yeah.
I mean, if you're trying to
Yeah,
but
but
if this is like
Scroll down slightly.
a smaller, like just a small snippet of data out of a much larger data
Yeah,
set.
see, I'm trying to predict
Right.
that
Well-
at x equals 11.
that's what I'm saying.
At x equals 11, it's 0.
Well, the assumption here, here's the thing. The assumption is you want to fit this.
What about x equals 20?
Oh, well, we'll talk about that later.
Well, think of it this way. Let's say you fit a line. Let's say you fit a line to this, and let's say it's a straight line.
Uh-huh.
And the next question is, okay, cool. So what is the value at 4? You're going to say 0. You're going to be way off. Basically, that line is absolutely worthless. At that point in time, you might as well just, roll a die for all it's going to do. You want something better to fit this.
Yeah, well, the engineer in me says sine of x near 0 equals 0, so, or equals x. So.
Once again, more conversations we need to have. Lots of conversations. But, huh?
It looks more like
Okay,
a cosine
yeah.
rather than sine.
Yeah, I pretty much added like sine, cosine, a little bit of noise. In fact, here's the code. Yeah. Basically, what I did was I went ahead and added sine, cosine, and threw in some random noise.
I was gonna say, that looked exactly like
No, it didn't.
the sum of two sine functions.
Well,
Oh,
yeah.
it's cosine.
2
Oh,
times
okay.
sine plus cosine of 3x, and then,
Cosine, sine, same
yeah,
Yeah,
then some noise.
I like it.
Yeah, cosine is basically sine just shifted. But the idea though is that if you want to actually perform any kind of prediction, it's not going to get you laughed out of the room. You're not going to use a linear regression. You
Okay.
need something that can kind of hit these
Line
oscillations.
sucks.
I mean, for some things.
Line size.
Or what if you just do
Problem.
a series of linear regressions where you like
Like
chop
a
it up?
piecewise linear regression.
Like a trapezoidal regression.
Would that do
Piecewise
anything for
linear
you?
regression.
And then piece up like
Yeah, you
Yeah.
put
can.
them all together?
But
That's less efficient, but like would
Oh,
that get
sorry,
it?
that would be
I'm
integration.
But the thing is,
Trapezoid.
I'm not interested in the piecewise. I want to know what the actual period of repeating of the. I want to know the period of the repeating pattern.
But you're right, Vic, that you could actually do, if you're interested in this case, like a piece, if you could figure out at what point the slope starts to go past a certain point, or when you maybe hit your maximum, I guess the point where, what is it, where your integral is like, the derivative is like 0, whatever, the slope at 0, then you can try to basically hit a series of like linear regressions to,
But then if you do that, you have to make a decision about which one of these half a dozen different, I guess, sections applies to whatever point in the future. Like where on this roller coaster do you expect this point to be? I mean, I guess you could try them all, but then you still have to decide,
Yeah.
all right, which one of these is likely to describe the
Yeah.
situation at that point in time.
Right, because there's the assumption here that this is representative of some phenomenon, right? And then we may get additional data, might be slightly different. So if we're doing something that's kind of piecewise, it may be a bit ad hoc just to try to overfit this data, right? And so, but there's an assumption, at least if we have more fundamental functions, even if they don't fit exactly, they're going to be more representative of the underlying phenomena. Yeah, there's a little bit of Platonism involved here, but we'll have that discussion after too. We have a lot of discussions we need to have. Oh, did I reconnect? Oh, well, I'm just going to run all.
Oh, yeah, right.
Make it
One
happen.
didn't pay the bill.
Yeah, I didn't pay the free collab bill. So,
If you have a bill that allows you to,
So that's a sine wave, huh?
oh yeah, there's actually a paid tier that gets you more.
that allows you to say, that allows you to, gives you dedicated CPUs.
Yeah. Well, for the stuff that I'm doing, I mean, it's good enough. It's good enough for you folks. No offense. But, no, but seriously, no. Yeah, the free tier is good enough. But yeah, but there are paid tiers. I love all of you, every last one of you. Maybe minus one of you. But yeah. So again, and so so Jared mentioned the cycle. And so yeah, so for example, we do have other shapes we try to fit, right? And of course, sine wave looks like a pretty good candidate because it has a nice little oscillating periodic behavior that we see some of over here, right? And so the question really becomes, can we maybe adapt a sine wave to try to fit this kind of oscillating data? And that brings us to the case study with Kai.
I just want to point out that actually attaching that RV increases the square footage, which was the
Yeah.
other variable.
I forgot to point that out, yeah, the number of bedrooms is like directly related to the square footage. Like you can't add a bedroom without impacting the square
Yeah.
footage.
You probably want to decorrelate those variables.
If you're really, really good, like handyman, you can do that.
Negative square footage.
You'll find a way. Okay, a good craftsman will find a way. That's all I'm gonna
I
say.
suppose so, yeah.
I don't let logic stop me from making points. Sorry, go ahead, Kai.
Yeah, you're introducing it. So in predicting the stocks, of course, he talked about the linear, the regression part. The regression part, and then when you look at the regression, a lot of times you see all this that's noise, right? But sometimes this noise actually doesn't seem like noise. It seems like it might actually be like some swirling thing around the regression. So the thesis I had was you first do a linear regression like Ahmed does, and after that you try to see if there's some kind of sine wave around this regression. And that will give you better fidelity in predicting what the stock might do tomorrow. And the way you can, so the actual implementation here. Originally this package was written for Node.js, it was an NPM package. But for the stock, I also wrote a edition for Python. And the package you can also download yourself. It's called SQL Map. It's just basically it's just basically the vanilla SQL-like. This vanilla built-in SQLite package with some extra added functions to allow you to do linear regression and sine fitting. So I'm going to show you a figure and just explain how it works. So this is just a regular SQL, standard SQL code you're writing, and the special secret sauce here is this special function right here. Sine fit extract and so they're custom SQL functions that added into the thing to help calculate the thing. And so we're going to go to this thing right here. So this is actually real data of the S&P 500. It's index that tracks it. It's called the SPX. The scaling is normalized, but it actually ranges somewhere from around 4,000 to 5,000. And this data is real data over 60 days, sometime recently during this year. I'm not sure which. I didn't label the exact dates, but it's data. So the first thing you do is you do a linear regression, like Ahmed said. And after that, all this noise, you try to see if you could fit this noise to a sine wave. So the package does that, and then these red dots right here are the actual predictions beyond the point. And then you try to backtest these predictions, see if these actual XRP correspond with these. So this would be Monday, Tuesday, Wednesday, Thursday, Friday, and then Saturday and Sunday you see are gaps because there's no data for those things. In the next figure, I'm going to show you actually calculating it day over day, the animation.
So, just,
Yeah.
the first step is the linear regression, right?
Yeah.
And then, so then you just subtract the linear regression.
The residue, yeah, I calculate the sine wave for the residues.
Yeah, you subtract the linear regression off of the data,
Yeah,
and then you compute a sine fit
yeah,
on that.
yeah. So you can think of the linear regression as maybe the long-term trend of the stock. Like maybe over well, 60 days back it could be, but maybe over a 10-year period you could see a linear regression trend of the stock. And you can think of the sine wave as a short-term trend. So you're trying to combine the predictions of both the long-term trend and the short-term trend, so you can get a better, more accurate short-term prediction. Basically, I want to predict what will happen to the stock tomorrow.
Yeah.
And then if it's going to go up tomorrow, then I might buy the stock today to hedge, to take advantage of that.
So it's kind of interesting because, like, if this works, right, it says that there is, like, locally in time, there is some kind of a periodic signal, right? Like, it's not noise.
Yeah.
Something that's-
At the very end, I do a statistical analysis just to test whether there's actually it's statistically significant. And the smaller it doesn't appear to be statistically significant. I'll show you the numbers a little further. So.
So I think there was like a Nobel Prize over like using Brownian motion or something
There we go.
to model the stock market. The Brownian motion was
So here you can actually see,
periodic.
in the moving window, as each day
I'm
passes,
not sure.
see, as each new data point from the next day comes in, it recalculates the linear regression, and then after the linear regression, it recalculates the sine wave. So you can see the prediction, the animation of these the predictions.
Those are the predictions. Oh.
Yeah, the red dots. And I'm only interested in the immediate one tomorrow. So I'm only interested in the first red dot. And that first red dot, yeah. This animation shows you the actual fitting process for visual. But when I'm doing this at scale, I'm actually doing a bunch of them. I'm doing like I'm doing about 200,000. I'm doing about 200,000 fits per every 60 seconds. And in order to do it that fast, actually there's a special algorithm that doesn't have to recalculate this whole fitting thing every time you move one data point. There's an iterative method that lets you calculate at least for the linear regression. You can just iteratively update the linear regression with each new data point. You have to recalculate the whole thing. And I could go into that later, but it's not included in this talk. We have time if you want to ask about that. And there's also an improvement to the sine fit as well. So the way the sine fit is calculated is the first thing you do is you calculate so you do the linear regression, and then you do a fast forward. When you do a forward, it's not fast. To get a rough estimate of where you think the frequency is in an integer, and then finally, once you get a rough guess of that, you again use these squares, but it's not because it's a nonlinear function. You have to use Gauss's method to do it. And I can talk about that as well if we have time. So if you draw that way and look only at the red dots, then this is what you get, right? So each dot is a prediction. So this is a prediction. Say this is today. This gray dot is a prediction for tomorrow. This blue dot, this thing is actually the actual result. Actually, this is a poor graphic showing the predictions. It turns out in this example right here, most of the predictions are wrong. So you start up here, right? Actually, okay, you start up here, and the prediction is it's going down, and then when tomorrow comes, it actually went down. So that was a correct prediction. So the next prediction is it's going to go down again. It's going to go from here to here, right? And then when next day comes around, it actually went down. So that's good. So I got 2 predictions right. Then the next day, you see this prediction is that it's going to go up, right? It's going to go from here to here. But the actual result was that it went down. So that was an incorrect prediction. And from here, this day, again, it predicted I was going to go up, but it actually went down. So that was wrong. Here, it was going to go up, but it actually went down. That was wrong. Here it was correct. It predicted it was going to go up, and it actually did go up. And here, it predicted it was going to go down, and actually did go. Those are correct. And here, it's kind of, you can't tell. It looks like well, you just say it's not going to change, but it went up, so I was wrong. And here it was going to go down, but it went up. And here it was going to go down, but it went down. Actually, so the prediction in this case, it looks like it was around 50-50 right. And the following prediction for tomorrow is it's going to go down again. And we don't know yet because we haven't seen it. And you can see this actually in motion. So each day I'm predicting, and then the prediction goes there, there, and there, and there. So that's Monday, Tuesday, Wednesday, Thursday, Friday. And then this is Saturday and Sunday. There's no predictions for those data points. So this is just for one single stock, or in this case, the SPX index. Like I say, I want to do it at scale. So I'm not going to show you scale for like actual 1,000 stocks, but this is you can imagine in your head. This is a visualization of 11 stocks doing the predictions for the red dots. Does everyone follow? Mm-hmm. Okay. And then finally, so this is basically the case study. And now I'm going to show you this actual statistical significance of the back test to see if this actually these predictions are actually meaningful. So in this back test, so yeah, each time I downloaded it. So the first thing I do is I download a SQLite database. This is already compiled database of SPX over the last 10 years. I'm not interested in all 10 years. I'm only interested in the last year. So the first thing I do is I grab data for the last 2 years because I need a starting point. Because I'm calculating the window, I need some leeway in the beginning to calculate to ramp up the prediction before I actually hit the 1 year mark. So first year is to just ramp up the calculations for the windows. And then in this case, the window I'm using is 45 days, approximately 2.5 months. And then once I get the predictions, you'll see the table. So this is the actual thing. So this is SPY, actually all the way from exactly 1 year ago, all the way to yesterday. So yesterday was October the 3rd, right? And this is a SQLite historical price of the SPX. You see. Okay, what you see here is okay, and this is okay. Yeah, this is the actual change. So as you can see, from day before yesterday to yesterday, the price, the market went down. So a -1. So when you see a -1, that means the stock market went down. When you see a +1, it means it went up. So these are the actual changes of the market from the previous day, and these are the predictions from these red dots, right? So each red dot is the prediction, and of course you see that these are actually correct. So yesterday I predicted it was going to go down, and it did go down. The day before I predicted it was going to go down, but it actually went up. So that was a wrong prediction. And before I did that, I should mention when I do these backtesting, to make it simpler, I just reduce the test to a binary outcome, whether the stock market is going to go up or down, because that makes it really easy to test. and when you have a binomial outcome, it's really easy to calculate the margin of error. It's just the square root of n. So the significance is basically this value right here. This is basically two standard deviations, assuming it's normally distributed. So if my accuracy is better than this thing, that means it's statistically significant. So if you count all the predictions over the last year, the accuracy is 65%. 65%. Or the bias over if you just pick randomly, 50-50 is 15% better than just random guessing coin toss. And as you can see, this 15% is higher than the error rate, so that's how I know it's significant. So the
What is
conclusion.
the error again?
What?
What is the error, the margin of error? Is that like the standard error?
No. It's you know when they do polling and sampling, but like you pick you're only given two choices, right?
Right.
Are you gonna pick Trump or Biden, right? And then they give you a sampling error. That's what basically is.
Is this derived from the binomial distribution?
Yeah, binomial distribution. So and then this is for the standard for the 95th at the 95th confidence level. So this is, which is basically two standard deviations, right? So this 15% means that it's greater than two standard deviations from what's expected, which means it's significant. It's not big. It's unlikely due to pure random noise. I think I confused you, but
No.
so yeah, you see the conclusion from that. Oh yeah, also if you want to know actually it already predicted for it's predicted for today. For today, it said it was going to go up. I didn't yesterday when I was calculating this, it didn't have the data, but it turned out that it was correct for today's prediction. And because I did this today, I don't have a prediction for tomorrow. But just so you know, in the training system, they actually did a thing. The prediction for tomorrow is that it's also going to go up. So we'll see tomorrow whether that prediction is right or wrong.
Oh, yeah. So did you use the iterative algorithm to do this one?
No, I calculated it myself. I can show you the source code actually.
Oh yeah, I was just
Okay.
wondering like the form of that calculation. Like you start from the beginning of the data, and then like for every day, right? You did this regression.
Yeah.
From the beginning?
No. There's a way you can actually update the regression without recalculating the beginning.
Yeah. No, that's what I mean.
Yeah,
Did you use that as you go along and then compare that to, like, consider the window up until the day, right, that you're gonna predict?
And then for tomorrow, I add a new data point.
Yes.
And I remove the old data point.
Yep.
So every time I move.
So it's a moving. It's a sliding window.
moving with sliding window.
Oh, okay, sliding window. Okay.
The one they have that on the internet, it keeps growing, but it doesn't remove the old one.
That's what I was thinking.
There's one that, and I figured out a way to do it.
I see.
While
So there's like some
removing
subtraction process that kind of happens from the calculation of the old.
The problem with this one is the one that keeps growing. It's numerically stable. So you could do it over 10 years.
Yeah.
It's the Welford algorithm. It works well. The one that I
Well,
figured out.
I'm imagining that it's some kind of streaming algorithm where it's like you're moving this, or you're just kind of continuously advising.
Yeah. The subtraction algorithm that I figured out is not numerically stable.
Oh, okay.
So if you start way back 10 years ago and go all the way, versus if I start from 2 years ago and go all the way, numbers actually come out a little different.
I see.
So you have to so you want to start as close as you are from the bit that you want, but you still need some leeway because you need to first pre-calculate the first 45 days.
I see.
Right?
Neat.
Yeah. And there's other performance tweaks for calculating the sine figures. The sine figure is a little more complicated.
Yeah.
Yeah. And fine. Yeah. So it's statistically significant, and I personally told you that tomorrow. I think the stock market is going to go. That's what they told me. But we'll see. And then the final thing is just the confusion matrix for those two. You know what it is. So these are the true negatives. So it predicted, so there were 74 predictions that was correct, that it predicted the market was going to go down over the last 252 trading days, or last year. So there's 252 total predictions for this year, for the window of this year. 74 of them were correctly predicted that the market would go down. 91 of them were correctly predicted that the market would go up. And then these are the false negative and false positive. So 54 were incorrectly predicted that the market would go down, but it actually went up. And 33 were incorrectly predicting that the market would go up, but it actually went up. And that's the case study. I guess questions. Oh yeah, I guess I can show you one. It's not in the collab, but it's that you can see the actual prediction, sort of. So when I do the prediction, I'm actually interested in both the long-term and short-term periodic way. So I do one for a short-term window. The short-term window it has to calculate every day what the optimum value. Right now it thinks the optimum is 45 days. For the long-term window, it currently thinks the optimum is 195 days. So this is the SPX over, I don't know what it's from, I think it's the 1 month SPX. No, it's a 1 year, SPX. And this is the sine wave it predicted over the short term. And each of these data point is a prediction point, it's not a fitted point. So that's why it's not a perfect sine wave. But as long as it looks reasonable like a sine wave, that means that the predictions are actually sort of not changing. And this is a long-term prediction of the sine wave. And this is the today, and this point right here is today. If you just look at a sine wave, the sine wave is telling me it's at the bottom of the period, so tomorrow we should be going up until it reaches the peak right there. This is just for the sine wave. And if you want to see the actual this is both the new regression plus the sine wave. Just the regular. So this point right here, so everything after this point right here is prediction. Actually, it's predicting combined that it's actually going to go down. But there's a bunch of other parameters I use to do prediction. Overall, the sum of all the parameters put together is this is going to go up.
What's the sort of architecture of the code you use for these predictions?
It's written. It's you start with a SQLite library, and then once you work out the map to calculate those things, you just code it up as a SQLite, as a SQL function, as extension, as a SQLite extension function.
And then do you write the code that?
You can actually run it in here. It's compiled into the WebAssembly, the actual Sine
Oh, I
function.
see.
So you could, if you want, you could actually write. It won't run off the top of my head, but you could do something like select.
Something I've noticed is that if you could do the sign fitting faster, in a sense, using phase lock loops. I don't know if you've looked into using phase lock loops.
Yes, I never heard of that. I'll look into that.
Yeah, look into it. It might be useful for your application. It's used for like demodulating FM radios digitally.
Okay.
It's a very fast algorithm for determining the dominant frequency.
Phase. That was fun.
Phase lock, yeah, see the wiki right there? Phase lock. But you can write, there's a digital version you use sampled data.
Thanks. This is just allocate to it. Yeah. And if you want to come into our case, show you the actual use for this line, use for scope for, or you just, well, if you you wanted, I can show it to you right now.
The source code?
But yeah, you want to see?
Sure.
Any other questions before I go into source code? Okay. So there's
Is that the tendency of pendulums to synchronize on it?
Yeah, people use that as an example, yeah.
Is that what it,
there's
is that kind of what that's like?
Kind of. So you have essentially a pendulum in software that syncs to the motions of the stopwatch.
Oh.
So this is basically the SQLite source law, the vanilla source law, and this is the actual. This is my custom exception.
You got 6 cylinders. You got like 2 cylinders, and then you got blank between them, or the rest on, and then you got a pendulum on. You have multiple pendulums.
Yeah, it
The
seems
pendulums
like
sync
yeah.
when it happens.
I think I've heard that they don't have to be on moving platforms.
Yes.
On the table.
Yeah.
Yeah, yeah. So
It takes the
what it
things at
does.
different periods and it syncs them up. It's really, I think, probably it's the new point of gravity or anything else.
So the first thing is it calculates. So the sine function is basically amplitude times sine of the frequency times time plus the phase, right? The easiest thing to calculate first is the amplitude, right? The amplitude is just basically the residual times of the square root, the r and root mean square of the residue. So that's what I calculate first. So this is the amplitude. It's just the root mean square of all the residues over the window. And then after that, I do that. I calculate the Fourier. I calculate the next Fourier transform for the next data point. And I remove the Fourier transform from the old data point in the moving window, right? As the moving window moves forward, I calculate it for the next window and remove it. So from there, I could get a rough guess of the actual frequency. So now I have a rough guess of the amplitude and I have a rough guess of the frequency. The only thing I don't have rough guess is the phase shift. But I don't need to get. I'm not interested in that. So that's and to get that because it's a linear thing. It turns out you can remove the amplitude because the amplitude is just a linear component, right? You have the sine function multiplied by the linear component of the amplitude, right? So I can remove the amplitude and just focus on calculating the frequency and the phase. And this is the algorithm to calculate the frequency and phase. And it's the Gaussian method. It's down here.
Gaussian method.
So this is the amplitude. It's equal. It also literally finds the amplitude off your own. So this is a Gaussian method for figuring out the amplitude. This is a Gaussian method for figuring out the intermediate variables. Once you have the intermediate variables, this is a Gaussian method to figure out the phase and also the frequency. And because it's an iterative method here, you have to do this several times. It's the best. And just from my personal testing, you iterate it about 8 times, I think. It's a quadratic estimation formula, so it quadratically converges to the best fit. Assuming, but it's a concave problem, so you're not guaranteed it, and there's some error correction code to when you're off it. So it does a Gaussian method 8 times quadratically to converge, and then once I do that then you find then you get the sine fit.
You mean it's not concave,
It's
or it is concave?
it's not concave.
Right.
It's not concave.
So
If it's not concave, then you use the window as the whole period, basically. So whatever your window is becomes the fiber, and from that you get the sine. And then if you want to actually run, and one because this is just a SQL function, like I said, you could just write it here. So it's the actual function to call it is Sine. Just these initial parameters you don't really need to worry about. Then you give it the t value, and you give it the actual y value. Select it from the SQL, where t is my time, my date, and y would be like my closing price rate. Yeah, that's how I would call it from SQL, from historical data. And what this thing returns is like a blob. It's opaque. It's like a C struct. And then you have to call special functions to extract the data you want from the Sine. So you call it like Sine extract. And I want to actually extract a struct, a C struct. From the C struct blob. I want to extract the prediction, the Sine fit predictions, which will be infer Sine fit, and you give it the value for tomorrow, for tomorrow's date. That's how we get the Sine value extracted. I'm sorry, this is mighty boring you. I'm sorry.
Does it bore me?
No, it doesn't bore me. I'm just not familiar with the SQLite API.
Yeah. And then for calculating these margins of errors and this accuracy bias. Okay. So finally, you have the as predicted. And you want to do your back test, right? You can do a select. And let's say you save all, you dump all this stuff as well. You create a table called predictions. Select. There's the backtest function is something called it's a binomial coin flip function. It's something like when and the predicted. Actually, you want the predicted change, right? You want the predicted. The sign. This is a binomial binary. I just want the sign, whether it's up or down. Is equal to the actual chain, right? This also returns a C struct. So it's conflict extract. Tell me to stop if this looks really cool.
So these are aggregation functions.
No, it's not. It's a window function. I'm sorry.
Oh.
So it's actually over.
Oh.
Over. You could partition. Well, there's no partition. If it was a table with a bunch of stocks, you would like partition by a stock symbol.
Yeah.
And
Yeah. Window functions are the limit of my SQL.
Yeah. So you order by PT. And so it's a window function. So
I've not done very much with window function. But that's how the calculation is structured. It uses the window function.
Rows between that's the window function. So for 45 days.
It's a very declarative way of saying it, but
So that's how we do the windows function.
the,
And then do you have something that
Over
uses this-
45-day window.
uses some
Yeah.
kind of automated software that then
Oh,
uses
man.
these queries to perform some action?
Yeah. So my bot is written in Node.js. Actually, the majority of the trading bot is SQL queries. And the Node.js is only for doing the high speed, for the high speed asynchronous HTTP downloading, talking, grabbing data from brokerages, and sending, posting orders, executions to the brokers. It's all SQL basically.
Right.
So the Node.js component is only for the HTTP.
Which SQLite library do you use for Node.js?
No, vanilla. No, I custom compiled it. I just took the vanilla SQLite, not Node.js from the vanilla SQLite, and I added my own custom Node.js bindings to it. So,
Oh, really? You have custom bindings?
So if you look at the source code. Actually, yeah, it was in here as well.
Oh, Node.js, it's just basically like JavaScript with the back and where the command line, like, do back and stuff.
Wait,
So this is that Node.js binding.
does it use a shim to send it over?
Huh?
Does it use a shim to send it over, or what does it do?
Yeah, how does the Node.js and the SQLite components communicate?
No, it's
Oh, is it because C
you
offers a...
use Node.js. Node.js comes with a build system for compiling extensions.
Okay.
Oh, okay.
So
There's a one-liner. One-liners of the dice. That's actually very functional.
And?
I just mean the sequel, the way that the sequel.
I thought you were talking about the one-liners.
Well, I mean, sequel technically is all one-liners. It is, no, it is, every single SQL query is a one-liner.
you're finding that this is just a big file. It's a make file. It's the equivalent of a make file, but for Node.js.
Yeah.
So you create this make file. You tell it the source files. So there's three build stages. The first stage is just compiling the first stage is compiling the SQLite database. The vanilla SQLite source code with my custom extensions. And the first stage is just building a custom SQLite. The second stage is to compile the binding. This is the binding part. Compile the bindings. And then the third stage in the make file is to link the SQLite library with the binding to create Node.js with C. And then there's all you have to do is create this make file, and then you just call the
Oh, MJS, is that make.js?
what I actually call it.
That's cool. I think this is just enough coding.
I'm sorry. Yeah.
I love it.
We asked you to use
I love
it. No, you're good, man.
I love it.
And I'm just interested in seeing how, like, this thing together. Thank you.
Okay.
Yeah.
That's it. And one more question, please.
Any other questions? Yeah, take that as a no, yeah.
Yeah, I agree.
Thank you. You did great then, you gave everyone what they asked for. Yeah, never promised you do what they asked for, right?
Yeah, I think I gave too much.
No, they asked, you gave, no, better give them too much.
That was
than
cool.
Seriously. You
Yeah,
did
no, that was great, Pat.
Yeah.
And there's a different binding to compile it to WebAssemblies. Because what you saw out there was the not Node.js, the WebAssembly binding.
Did you make the web console and everything?
Yeah, yeah,
The editor?
yeah. And yeah, that's everything is scratch.
Did you-
There's no dependencies except for Node.js, and there's no external dependencies except Node.js.
So that online, that console you have, that's WebAssembly, right? Or where it was, the site?
So, this is the actual WebAssembly bindings. And if you want to compile it, you know, in Linux you compile something. In Linux you just type GCC something, right?
Right.
So there's an equivalent for GCC for web. It's called EMCC.
Oh,
So it's almost the same as compiling for GCC. You just type EMCC, the files, the C file you want, and then.
So you're compiling the C code to WebAssembly, and that's what's running on the website.
Yeah.
I see.
So there you can see EMCC. You can think of EMCC. You can think of it as just GCC. So EMCC, a bunch of WebAssembly compile options, and then I specify the binding. This is the JavaScript binding for the WebAssembly, and these are the object files. So the object files are again EMCC. So I compile the SQLite vanilla file with my custom SQLite functions, and it's again two those things. First, call EMCC first to compile the object files, the SQLite, and then finally call EMCC again to link them to the binding, the WebAssembly binding.
So do you have some kind of like a web page generating code that you wrote in C that's compiled like this? Or do you use some kind of framework to shrink the website?
So this is the bind. So I show you the wrapper file, right? Once you compile it, it'll spit out two files. So
It goes like an HTML file that hosts edited and injects the WebAssembly, right?
So this is the actual WASM binary. It's just a binary file. Okay. It is a C object file, so it's in WebAssembly, and this is the actual binding that EMCC spit it out. You can look at the actual file. So this is actual compiled JavaScript binding that is spit out. So you need two files.
Unified.
You need the JavaScript binding that EMCC spit out, and you need the actual the WASM file. Right? And it's a binary file, so it won't show it. It just downloads it. And this editor is it's also just one file. Yeah, this is a front end file. This entire file, which is about which is how long? Oh, I'm sorry. This is the edited file. It's external file. It's called Mirror. Have you heard of it? Okay. It's open source editor. So this editor you see is actually that file. It's called Mirror. But these But these visualization charts and all this UI stuff is actually is this file over here.
Single page apps.
Here you go. This is file. So aside from the editor, the whole front end is this. How many code?
What are you looking for?
For 4,500 lines. For the 5,000 lines. It's a single bar. These are all the resources downloaded to this. So this is a front-end file. 5,000 lines. Is there like
Some equivalent of CMake?
Huh?
Like an equivalent
Yeah,
of CMake, but for
no, it's
WebAssembly?
you have to do EMCC.
Oh.
No, it's called EM scripting.
Oh, okay.
So EMCC is the GCC equivalent.
Yeah.
Is the EM scripting equivalent for GCC? There's no make files though.
Yeah.
I don't know. Actually, there is. I think I forget that. Yeah, but I don't use it. I just use C. I don't do C++.
Oh.
It's all in C.
Yeah, that's pretty cool. I never heard of anybody using a compiled C for a web app. That's kind of neat.
Well, SQLite is. Yeah.
Yeah, so you need it.
Yeah.
Yeah.
Although they now have a WebAssembly API. This project was created
Oh,
before the WebAssembly API came out, so it's all written from scratch.
That's
Or maybe I scared you.
No, it's good. No, in fact, I was actually watching a video on like seeing WebAssembly. It was kind of nice to actually see something written in it. The guy was trying to do a game in it, and he was going off the deep end with a lot of stuff, so it's cool to kind of see this.
Guy, have you considered rewriting this in Perl?
Don't take the bait. Don't take the bait.
Are you offering something other than just email? Are you offering a trader position for CPL? Is that the next growth? Is that the next growth model?
Your prediction is accurate.
Awesome.
It's only a matter of time before it gets to fun from Node.
So that's this
Oh,
one.
and the PyTorch again.
Oh, sorry. Do you want me to pop it open again?
Most people use Python.
I mean, we chose that in Python just because of the notebooks, but in reality it varies. But a lot of people are doing basically JavaScript and then something in the back end, often C# or Java, but you know, it's all over the place.
You just download it. Just VIP install. It's already pre-compiled. If you're running, it's already pre-compiled for Linux, Windows, and for Linux, Windows, and Mac OS.
This is your pip package?
Yeah. So you just have to. You don't have to compile it when you install.
Oh, okay.
Awesome.
Yeah. I want to learn more about SQL window functions.
But yes, SQLite is. You don't need another language to your business block.
It's pretty cool. I've started using it in my projects at work. SQLite.
Awesome. So thank you. You can hang around here. Next month, Garrett's going to be doing the fast Fourier transform, right? So definitely, yeah, looking forward to that one. I was looking forward to this one too, so it was great. So definitely join us, and we're going to hang around here and shoot the breeze, nerd out, or whatever. But we're officially done with the,
Make sure.
talk portion of it. Not for this guy. Really good stuff. Thanks, Kai. It was awesome.
Oh, I'm clapping for Kai, not for you, sorry.
Get out of here, man.
I love you too.